The recent controversy over plans to drill for gas off the Otago coast has highlighted the need to find alternative and clean energy sources. Some of that work is being done in Dunedin, with researchers looking at the possibilities of harnessing the energy of photosynthesis. That could involve, of all things, pond scum. Professor Julian Eaton-Rye joins us tonight to tell us why. Good evening.
Good evening.
Tell us a bit about your exciting research. What does it involve?
Well, I've always sort of had an interest in photosynthesis since an undergraduate, and I've thought about how sunlight's used to fix carbon dioxide into sugars. And that process requires electrons that we get from water. So I got interested in how you can split water to get oxygen and hydrogen, and then from there thought of a way to study that and chose pond scum as the model system. And then it turns out pond scum are very useful sort of solar energy mini factories to make things, and so we've begun to exploit that to make useful products.
What success have you had so far?
In the first area of actually thinking about how photosynthesis splits water, we've made some discoveries in protein factors that help us understand how plants build the machine that does it, and that has implications for making chemical machines that can do the process artificially. But in the case of the solar factories, we've tried to make butanol from our cyanobacteria. And we've had some success at getting sunlight to turn carbon dioxide into butanol rather than ordinary sugars.
So what more needs to be done before commercial production is a possibility?
For butanol, the big question is, can you increase the yields? So you can make it happen, but you need to make it happen on a commercially viable scale. So scaling up is the big challenge. And in the case of splitting water, there you will get hydrogen as a product, so you'll have another fuel there. And the actual mechanism by the way plants achieve it is yet to be fully understood. Remember, plants do it at ambient temperatures. Today in Dunedin it's about 15, 16, and plants are very happily splitting water, and they will do it at 4 degrees. But if you and I wanted to do it, we'd have to heat it to 2,000 degrees. So understanding how the plant does that and then turning that into an application where we can make hydrogen from water is the key.
How confident are you that this research will lead to a sustainable alternative to a fossil fuel?
Well, more energy strikes the Earth in 1 hour than all humanity uses in a year. So there's a big resource there, and I think people will want to tap into it. So I think just the very fact that opportunity is there, as we see declining fossil fuels, will drive people to exploit these technologies. The tools that, in terms of molecular biology to do it are already here. So it's a question of investment and going for it.
What are the benefits of such a fuel?
If you think about it, it's not just fuel that you can make. Fuel is definitely one thing, and butanol can go directly into the engines that we have now. But you can use these little cells to make solar-powered feedstocks for anything that would have been originally dependent upon hydrocarbons. And given the fact that there are about 7 billion of us on the planet, and we increase, I think, at 150 a minute, so that's about 78 million more a year. All those people are going to want resources, and this is one way in which resources can be put on the table for them to feed them and provide fuel for them and medicines and pharmaceuticals.
Any downsides?
I think the first downside is that there is a need for investment, and I think the investment will be considerable, and this will require the price of oil to go higher than it is. So there's going to be, when are people going to jump and really push for it? And for the public, there's always the catch that these organisms are genetically modified. For example, we take genes from an organism called Clostridium and put them into our organism, and that helps it to make butanol. So you have to get over the perception issue that genetic engineering may be a difficult issue.
If cyanobacteria was a practical alternative, what would be the practicalities of producing it?
Well, I mentioned that they would be genetically modified. This is fortunately overcome by the fact that you would actually grow them in large vats, and so they would be self-contained, and they would not be able to survive outside of containment. The economic input would require lighting, and then the ability to condense the gases that came off, whether you were using it to make hydrogen or whether you were using it to make butanol or ethanol or some such compound.
Well, it's an exciting prospect. Good luck with your research.
Thank you.
Professor Julian Eaton-Rye, thank you very much for your time.
Thank you.